Good afternoon, and first I'd like to welcome to the unusual time of the Colloquium, and I'd like also to thank you to welcome. And I'd like to introduce our lecture today, and it's a special lecture. It's a distinguished lecture invited by the Wigner Foundation. And today the speaker is Professor Serge Haroche. Serge Haroche has obtained his study in École Normale Supérieure in Paris, and he also obtained his PhD in University of Paris. He has been postdoc and guest researcher and guest professor in different universities at Harvard, Stanford, and also at Max Planck in Garching and Yale University. And he obtained several awards, and okay, I have a long list of these awards, but I choose some of them. It's one of the latest is the highest award in France given by the Centre National de Recherche Scientifique in the CNRS in France. That is the gold medal. He obtained it in 2000 and 2009. And yes, and Professor Serge Haroche will speak today about quantum feedback control of non-classical microwave fields in cavity quantum electrodynamic experiments. And Serge,
thank you. Thank you very much. So I would like first to thank the Wigner Foundation and the French-Swedish Association for Research for having invited me and giving me the opportunity to visit, to interact with colleagues here and to talk about our recent research in Paris. In fact, the title I gave to my talk might seem a little bit technical, but I want to give a general, to take this opportunity to give a general view of the cavity QED experiments we are performing in Paris. What we are doing basically is to trap a quantum field in a box, which we call a photon box, and to demonstrate with this very simple system fundamental aspects of quantum measurement and quantum physics, with the hope that there might be some applications in what is known as quantum information science. And the latest development of these experiments is the demonstration of quantum feedback, that is, the use of feedback methods applied to quantum systems. The kind of experiments we are doing are very simple in their principle. We have a quantum field which is trapped between two mirrors, and this field is interrogated by a beam of atoms which cross the cavity one by one, and single atoms interact with the cavity field, and they get information. They take a kind of imprint of the cavity field, and we get this information when we detect the atoms. Usually, when atoms are used to detect light, it's done in a very brutal way. The atoms are absorbing the energy of the photon, and we get photodetection. In the experiments I will be describing, this interaction is much more gentle. The light and the atoms do not exchange energy. There is only a phase shift which is imprinted on the wave function of the atom, and this is a much it perturbs the light field in a much gentler way, and we will see that it leads to interesting possible applications. In fact, this method, which detects light without absorbing the photons, is called quantum non-demolition. The quanta of light are not destroyed, and we get information from the light without destroying the light energy. So it's a new way to look at light, and it has opened many new perspectives in quantum optics. For instance, we are able to count the photons which are present in the box. You cannot see it very well here, but you can see steps through which the light is escaping from this box, photons escaping one by one, and so we can count photons in this way. We can also use these methods not only to count the photons, but to prepare and reconstruct non-classical states of radiation. And here, for instance, you can see a kind of 3D map, which is called the Wigner function, of a special kind of photon field, which is a Fock state, a state which has a well-defined number of photons. This Wigner function is a representation in the phase space of the field, in a space which is referred to two quadrature of the field, and it's a kind of probability distribution for these quadratures, a little bit like a harmonic oscillator can be represented in its phase space by giving the probability of a value of x and p. Now, in a quantum system, of course, you know that you cannot measure x and p with accurate precision due to the Heisenberg uncertainty principle, and the result of that is that these probability distributions can take negative values. You see here, for instance, the blue color represent negative values of this Wigner function, and you see that the Wigner function of the Fock state is represented by rings taking alternatively positive and negative values. And this negativity is a signature of the non-classical nature of the field, and it's related to interference effects. Another kind of non-classical fields we are able to prepare and reconstruct are called Schrödinger cats. These are superposition of two coherent fields, two fields with well-defined phase, but opposite phases. Each of these fields is represented by a Gaussian peak in phase space. So you have here one component, here the other component. And in between, you see fringes taking alternatively positive and negative values. And these fringes just express the fact that you have a coherent superposition of the two fields with opposite phases. And these Wigner functions are also a clear indication that you can prepare non-classical state of the field using these methods. Now, usually, these non-classical states of the field are very interesting for quantum information because they are very fragile features. The quantum interference that you have in these states could be exploited in various ways. There are potential resources for quantum metrology, for quantum cryptography, and also for quantum computation. And they are useful, but the price you have to pay for that is they're hard to prepare, and they are very sensitive to decoherence. For instance, we have recorded here on a movie by taking snapshots of the Wigner function at increasing times after the preparation of the state, the decoherence process in action. You will see in this movie, or you have already seen, that these fringes vanish as a function of time. I'll try to show the movie again. You can see here how the fringes vanish, and here you have the time scale. And this is decoherence as it occurs in this system. So when we have reached this stage in this research project, our goal was to try to use the techniques of manipulation of these quantum fields in order to fight against decoherence, to use the atoms to observe, to make a diagnosis of the decoherence process, and to use this information to feed back into the field and correct for the effect of decoherence and restore the coherence in the quantum system. So I will describe this experiment at the end of my talk, and I will show that we can, in real time, use quantum feedback methods to prepare and stabilize Fock states of light, which are non-classical, and we have some ideas to extend this to other non-classical states, such as the Schrödinger cats. You see here the density matrix for a coherent field. This is just a matrix showing in two coordinates n, the number of photons, and you see that the coherent state has a lot of off-diagonal elements everywhere, and when you prepare a Fock state, you just have a peak on the diagonal of the density operator. So I will show how the quantum feedback methods can be used to prepare from this state, that state, and how we can stay in that state using quantum feedback. But first of all, I have to remind you or to tell you about our experimental setup and our experimental methods. The main ingredient in all these experiments is to be able to keep the field in a very high Q cavity for a very long time. So we need a box, photon box, with walls which are perfectly reflecting, which allow us to isolate the field as best as we can from the outside world. And this box is made of two mirrors which are facing each other, two spherical mirrors, which are coated by a thin coating of niobium. And the mirrors are cooled to very low temperature, less than 1 Kelvin. Niobium becomes superconducting and perfectly reflecting. And so the light can bounce between these mirrors for a very long time. And atoms are crossing the cavity one by one. So the system we have is very simple. We have one mode of the field, let's say 1 or 2 photons bouncing back and forth, and just one atom coupled to this light. Now these mirrors are very special. Their reflectivity is so high that light bounces more than 1 billion times between the mirrors before decaying, and a light beam is just folded over 40,000 kilometers, so corresponding to the Earth's circumference, which means that the photons are trapped for more than 1/10 of a second inside this cavity, which leaves a lot of time to perform experiments. The photons are bouncing on the mirror, they pass many times on the atom, and this enhances tremendously the light-matter coupling, which is the essential feature about cavity QED. And the experiment is going this way. The atoms go one by one, and then they are destroyed in the end, and by destroying the atoms, we get the information we want about the field inside the cavity. Now, of course, this is not performed with just any atom. We need atoms which are very sensitive to the coupling to microwave radiation, and we use what we call circular Rydberg atoms. These atoms have a high principal quantum number. The transition we are studying occurs between n equals 50 and 51. We'll call E this state and G this state. And not only they have a high energy, but they also have a high angular momentum. In fact, they have the maximum possible angular momentum, which means that the electron is rotating around the core on a circle. This is why they are called circular Rydberg atoms. These atoms have very interesting properties. First of all, they are giant atoms. Of course, the size of the orbit is thousands times larger than a ground state atom. They have very long lifetime, so the dissipation is very weak. The lifetime is comparable to the lifetime of the photon in the cavity, 30 milliseconds. And they correspond to huge electric dipoles because the distance between the core and the electron is very large. So they are very sensitive to microwave radiation. And also, very importantly, they behave as a two-level system. You can forget about all the other states of this atom and consider only the evolution of the system between these two states, E and G. And as we know from quantum physics, a two-level system can be described as a spin. And so the spin picture will be very simple and very convenient to describe the evolution of the atom in the system. The price we have to pay for this is that the preparation of this state is not that easy. It's a complex process involving absorption of laser and micro radio frequency photons by the atoms. And also these states are very fragile, and you need to keep them in an electric field. The electric field is used to prevent this circular state to be mixed with states with low angular momentum. And so this explains why the cavity must be open. We could have considered closed cavities. We could have a very high Q, but in a closed cavity, the electric field is zero, and the circular Rydberg states would not survive. So this explains the main point of this atomic system, and you can have more details about the preparation and properties in this reference. Now, just a few words about this two-level, this spin picture. We know from nuclear magnetic resonance, for instance, that the spin picture is very handy, and that this spin evolves on a sphere which is called the Bloch sphere. The two states, E and G, correspond to the polar axis of the sphere, spin pointing of this sphere, spin pointing up or down. And when you prepare linear superpositions of E and G, it amounts to performing a rotation of on this Bloch sphere, and which rotates states E on E plus G, and we get into the equatorial plane of the Bloch sphere. In fact, the sphere should be seen. I don't understand why you don't see the sphere, because I can see it on my screen, but you can imagine that there is the sphere here. And so when you prepare a superposition of E and G in the equatorial plane, and you let it evolve as a function of time, you get this spin is rotating along the equatorial plane. To prepare this spin, you apply just a microwave pulse, which rotates from E to E plus G. Then this superposition rotates at the frequency of the transition between E and G. And we like to think of this rotating spin as a hand of a clock, which is measuring time. In fact, it's an atomic clock. It's a Rydberg clock. And by measuring the time given by this clock, we will get information about the photon number in the cavity. Why? Because the atoms, being off-resonant, cannot absorb light, but they undergo energy light shifts, and the spins are delayed by this light shift effect. And you know that light shifts are proportional to the field intensity, that is to the photon number, and the sensitivity is so big that one single photon can make the spin hand miss half a turn during the time the atom crosses the cavity. So there can be a phase shift of the order of pi per photon, and this shows that the system is sensitive to single photons. The phase shift per photon can be adjusted by changing the atom cavity detuning, by just applying an electric field across the mirror. By Stark effect, one can shift a little bit the energy levels and detune the atomic transition by a well-defined amount from the cavity mode, and in this way control the light shift. Another way to look at the light shift is to look at the energy levels. Two important parameters here: the vacuum Rabi frequency omega, which describes the strength of the coupling between a single atom and the cavity mode, which depends upon the position Z of the atom across the cavity, and the atom cavity detuning delta. If the atom is non-resonant, the two levels E and G will experience light shifts in opposite direction, and you see that the energy levels will be split by a different amount inside the cavity, different from what it is outside. And as the atom crosses the cavity, a superposition between state E and G will undergo a phase shift, which is just the integral of this energy shift over dz over v, which is a time differential here. And you see that the light shift is to lowest order proportional to the square of the coupling and inversely proportional to the detuning. And this factor here can be called phi naught. It's a phase shift per photon. To lowest order, we see that the phase shift is proportional to the photon number. There is a phase shift per photon. So by measuring this phase shift, this amounts to counting the photons. And it's a non-destructive counting because the atom which crosses the cavity does not absorb or emit photons. In fact, this is an important point here. The phase shift is adiabatic. If the atom is in state E, it will follow adiabatically this state, and the probability to go from E to G or from G to E is completely negligible, even if you are close to resonance. I also want to stress that the atomic phase shift, which is induced by light, is reciprocal from the light phase shift induced by the atom. And a light phase shift induced by an atom is a well-known effect. It's called an refractive index effect. In fact, it means that our experiment is sensitive to the index effect of a single atom. In fact, all these experiments express the fact that a single atom inside the cavity has an effect on the phase of the light, and that a single photon present in the cavity has an effect on the phase of the atom. And this is the signature of this, what we call the strong coupling regime in cavity quantum electrodynamics. Now, to measure phase shifts, the method is, of course, atomic interferometry. If you want to measure how the phase of an atomic wave function evolves, you do interferometry experiment. And the standard interferometry experiment in this domain is called the Ramsey interferometry. And this is a Ramsey setup. You see here in the middle the cavity which contains the fields that you want to measure. This is a box where the circular states are prepared. They drift one by one across the cavity, and here they are detected by field ionization. And the field ionization tells us whether the atom is in state E or G in the end. Two major ingredients here are the zones R1 and R2, which build up the Ramsey interferometer. In R1, a pulse of microwave prepares the superposition of E and G, which then evolves across the cavity. And here a second flash of microwave is used to detect the phase of this superposition after the atom has crossed the cavity. And this succession of two time-separated pulses applied on the atomic beam is, of course, known as Ramsey interferometry. And this is a technique which is used in all atomic clocks. This is just an atomic clock that we have here. The specialty of this clock is that we store photons inside the clock. So we just have an atomic clock which is delayed by the photons which are trapped inside it. And this clock is very sensitive to light because it's built on Rydberg atoms. So we used first this system to count photons, and I will say a few words about this experiment. In fact, this experiment illustrates fundamental aspects of quantum measurement, and I will show you that in fact we can witness the collapse of the wave function, so to speak, in real time in this experiment. Let's suppose first that you want to detect whether there is 0 or 1 photon inside this box. We use a single atom. This atom arrives in zone R1, and then a pulse of microwave field is applied to it and prepares a superposition of E plus G, which is just a spin or atomic dipole pointing in a given direction. Once this dipole has been prepared, the atom crosses the cavity and accumulates a phase shift during the crossing. Then this is measured in R2, where a second microwave pulse is applied to the atom. The phase shift per photon is fixed equal to pi, which means that if you have 0 photon or 1 photon in the cavity, the effective spin will point in one direction or in the opposite direction. So you have here two orthogonal states which are correlated to the absence of photon or to the presence of 1 photon in the cavity. But you cannot measure directly G plus E or G minus E. What you can measure are G and E separately, the energy states. So that's what you do in the second Ramsey zone. You apply a microwave pulse which masks G plus E back into state G and G minus E back into state E. And now what you have is a perfect correlation between the atomic states E or G and the photon number 1 or 0. So this is the basics of the measurements of the photons. If you want to do it experimentally, it's very simple. You don't have to do anything. You just have your cavity here, which is empty, and you wait. And since you are not at 0 degrees, we are at 0.8 Kelvin. According to Planck's law, there is a 5% probability that a photon will pop up in the cavity and stay for 5% of the time in the cavity. So what you have in this system is a photon which is blinking in and out with 95% of the time the cavity being empty. And to detect it, you just send atoms one by one, fire the Ramsey zones, and then in the end detect the atom and ask the detector, do you find E or G? And you see here the result in the next slide here. You see here a time scale in real time. So it's 1 and 2 seconds. A blue bar represents an atom detected in level G. A red bar, an atom detected in level E. And what you see is this kind of trace, which shows you clearly that something happens here. This is the appearance of 1 photon in the cavity, and then the photon disappears. There is some noise because the fringes of the Ramsey interferometer have not 100% visibility, but it's quite clear that the photon has appeared and disappeared here. If you blow up this zone, you find that there is a quantum jump here, the appearance of a photon, which can be marked at this point. And you also can see that hundreds of atoms here see the same photon without absorbing it. So it's a quantum non-destructive measurement. So this is what we can do if there is only 0 or 1 photon, which is the simplest case. The next question is, can we use this to measure an arbitrary photon number with number of photons larger than 1? First of all, you have to prepare this in the cavity. And the way to prepare a larger field in the cavity is simple. What we do is that we have a horn here, a classical source of microwave, and we apply a pulse of microwave inside our cavity system. So the photons are everywhere, but a small number of photons are scattered on the edges of the mirrors and get trapped inside. Then we switch off our source, and this field stays for 1/10 of a second, and by just adapting the length of this pulse, we can decide how many photons on average we trap in the cavity. I say on average because this field is a classical field. It is produced by a classical source, so it has a well-defined phase. And there is an uncertainty relationship between the number of photons and the phase. Uncertain delta n, delta phi larger than 1/2. If delta phi is very small, it means that delta n is large. And in fact, these classical fields, which are called Glauber states, because Roy Glauber did the theory of quantum optics in the early 60s and described these states in detail, these states have a Poisson distribution of the photon number. The probability to have n photons is given by a Poisson law, whose mean value corresponds to the average number of photons in the field. So the photon number is fuzzy, but we will measure it. And in a quantum measurement, when you have a fuzzy quantity that you measure, of course, you pin it down to a single value. So that's exactly what we will do. And in fact, this, as I will show, this spinning down will occur progressively. So again, now we can go a little bit faster. This time we choose a phase shift of photon equal to pi/4 because we want to have 8 different directions in the equatorial plane of the Bloch sphere. And again, we send an atom. When the atom reaches R1, we apply a pulse of microwave, so we prepare a superposition. We let this superposition drift across the cavity, but you see this time we have a fuzziness in the light shift. The light shift can take different possible values, which means that after the atom has crossed the cavity, the system can be in 8 different possible states, and for each direction of the dipole you have a different photon number. And if you look at the wave function of the combined atom field system, you have entanglement. You have an entangled wave function where the photon number is entangled with the direction of the atomic spin. And then you have to resolve this entanglement, and this is what will happen in the second Ramsey zone. So you apply a second Ramsey pulse, and what will this second Ramsey pulse do? What it will do is that it will map one direction in the equatorial plane of the Bloch sphere back into the energy direction. For instance, it will map this state n equals 0 into G, and the opposite state n equals 4 into E. But you see immediately that you have a problem. If you have 6 photons, this state will be a superposition of E and G, and when you will detect, you will randomly find one value or the other. So this means that a measurement which yields only a binary information cannot allow us to distinguish with a single atom more than 2 n values, which is obvious. So the solution, of course, will be to send more atoms and to accumulate information. But before that, I just want to show you what happens when you detect in the second Ramsey zone. You have here all the spin direction in the equatorial plane of the Bloch sphere, and the second Ramsey pulse does a pi/2 rotation along an axis, which will map the equatorial plane back into a meridian plane, and you see that this one direction, the blue-red direction, will be mapped into the energy. But all the other directions will remain superpositions of the energy. This kind of pictures tell us something very simple. The second pulse, followed by fidelization, realizes a measurement of a transverse spin component, and the direction that you will project onto the z-axis depends upon the phase of this pulse, the phase of the second Ramsey pulse with respect to the first one. And this is a knob that you can adjust. You can change the phase of the second Ramsey pulse, and in this way decide which direction, this one, or that one, you project along the energy axis. So what does a single atom detection do? Suppose that at the beginning you don't know what the photon number is, so you have to start from a flat distribution where all the photon numbers have the same probability. And suppose that you decide to detect along this axis, which corresponds to the 0, 4 photon axis. And suppose that you get the atom in state E. It means that you cannot have 4 photons, because if you had 4 photons, the probability to get your result would be 0. So in fact, what happens in this case is that the probability to have 4 photons has been decimated, cancelled, and you have a large probability to have either 0 or 8 photons. On the other hand, if you had detected the other spin direction, the probability distribution will be changed in this way. So what this tells us is that a measurement changes the knowledge that you have about the system and changes the probability distribution that you can infer after the measurement has been done. In this case, a single atom performs a quantum non-demolition measurement. In fact, the operator which is used here is called a positive operator valid measure in technical terms. And what this does is to multiply the photon number distribution by a sign function of the photon number. And then you go on, you keep sending atoms, and for each atom you can decide along which direction you detect. And each time you detect an atom, you multiply the previous photon number distribution by a cosine function whose phase depends upon the random outcome of the measurement. And you see immediately, if you keep multiplying this cosine function with each other, that after a large number of atoms has been detected, the photon number distribution converges to a Dirac peak for it. Only one photon number is left. And this experiment shows in real time how the wave function collapses. In fact, the measurement is an acquisition of information. And since you acquire here the information step by step, atom by atom, the collapse occurs atom by atom. And in the end of the process, which requires a few tens of atoms, you end up with a well-defined photon number. You see here two realization of the experiment. You see here the initial photon number distribution, how it evolves in time, and in this case it has converged to 5 photons. If you do the experiment again with the same initial field, in this trace it has converged to 7 photons, and so on. And if you do thousands of such experiments and reconstruct the histogram, you reconstruct the Poisson distribution of the initial field. So this kind of experiment is an illustration of all the postulates of a quantum measurement. The collapse of the wave function, the fact that it's repeatable, because if you keep it, once you are in an eigenstate, you stay there, and the fact that the system reconstructs statistically the distribution which is imprinted in the initial wave function. At this point, I want to make a remark. This kind of measurement, it's a measurement, but it's also a preparation. You can think of a measurement as a filter which allows you to prepare the eigenstates of the operators that you are measuring. So by this experiment, we prepare Fock states. The only problem is that we prepare them randomly. When you do a run of this experiment, you don't know a priori which Fock state you will prepare. And if you want to prepare a given Fock state, you have to resume the experiment a large number of times until just by chance you fall on the right one. So the question we ask ourselves is it possible to modify the procedure in order to drive the result toward the pre-selected Fock state? Since you acquire information progressively, is it possible to use this information to feed back a field into the cavity in order to steer the field towards a well-defined direction? And once you have reached this well-defined photon number, is it possible to use this continuous observation to prevent the system from jumping, or at least to correct the jumps? Once a jump has occurred, immediately to add or subtract a photon to come back in a steady state into a given Fock state. And this leads us to the quantum feedback part of this talk. We published this very recently in this reference. And we like to describe this experiment by this kind of drawing. In fact, what we are doing in our experiments is juggling with photons using atoms as probes. And it's a very subtle juggling game. And in fact, any juggling game is a feedback experiment. When you juggle with balls, you need your eyes to follow the motion of the balls, and from what your eyes see, you react by changing the motion of your hands. And of course, this has to go through the brains, which interpret the information and send it to your hands. A quantum feedback experiment is about the same. The balls will be replaced by photons bouncing between the mirrors. The eyes are replaced by the atoms, which looks at these balls, and the hands will be some kind of feedback field which will be injected in the cavity. And of course, we need a brain. The brain will be a computer, which is hooked to the experiment. But there is a novelty with respect to this classical feedback. The fact that by just merely looking at your balls, you modify their positions. This is just a back action of a measurement. And we have to take this into account. We have to take into account that the mere fact of measuring and observing will perturb the system. So this is an introduction to this real-time quantum feedback. I just want to say that we perform this experiment in collaboration with a group at École des Mines, which is a theory group of mathematicians who are working on the feedback of classical systems, the feedback control of classical systems, feedback control of machines, of airplanes, of motors, engines, and so on. And they were very much interested in developing algorithms which take quantum physics into account, and they were very helpful to help us design the algorithm we are using in our experiment. I remind you the two problems we have to solve. Can we make the progressive QND process deterministic and prepare a given Fock state and not just a random one on demand? And can we counteract decoherence-induced quantum jumps and stabilize Fock states in steady-state operation? I remind you here how a classical feedback loop works. Usually you have a system, for example, the temperature of an oven, the velocity of a car that you want to control. You perform a measurement of the quantity that you want to control with a probe system A. And this measurement gives a result S that you compared with a target value S0. This comparison is performed by a computer. And the computer gives an order to an actuator B here, which applies a correction which is proportional to the distance between the actual value of the signal and the target. You have a gain factor here, and this operates in closed loops. And this is what you do in the for the thermostat of an oven, for the velocity of a car. So sometimes it's simpler. Sometimes the feedback is automatic. For example, in the Watt regulator of steam engine, you just use the centrifugal force as a kind of analogic device which performs the correction without having to do any computation. But in most cases, the feedback, especially in modern technologies, the feedback involves these separating gradients. The sensor, which measures the signal, the actuator, which applies the response, and the link is made by a computer, a classical computer. So, as I said, to generalize this to quantum system is challenging because the measurement in itself has a random back action system state, and so the computer should be intelligent enough to know quantum physics in order to take into account this back action, to take it into account before it applies the correction. And the solution we have found is to perform QND weak measurements, that is to use atoms. If you send a single atom across the cavity, it gives you a partial information about the photon number, and you use this partial information that we can call a weak measurement to estimate in real time how the state of the system has evolved, knowing this result, and knowing the state of the system to apply the optimal correction which brings you as close as possible to the target, and do it again and again, atoms by atom. So this gives the recipe here. What are the components of our feedback loop? The sensor, the probe, is a quantum system. These are the atoms which cross the cavity, and the quantum measurement, which is performed in R2 and the detector. So this is our eye, the eye which is looking at the field in the cavity. Then the computer, the controller is this computer which gets the information from the measurement and which gives an order to the third part of the system, which is the actuator. And the actuator is a classical source of microwave, which injects by diffraction on the mirror's edges a small classical microwave field inside the cavity. So these are the ingredients. And now, what is the protocol? How does it work? We start by, the only thing we know how to prepare simply are classical fields. So we start by injecting a coherent field inside the cavity. Then we send atoms one by one across the Ramsey interferometer, and we detect each atom projecting the field density operator, the state of the system, which is technically described by what we call the density operator, in a new state, which is estimated by the computer, knowing the result of the measurement. Once the computer has produced the new state, it computes the displacement, how big should be the field applied here, which minimizes the distance between the target and the new state. And we have to define what the distance means in the Hilbert space, in the space of quantum states. Then we close the feedback loop by injecting the field which has been calculated here inside the cavity, and we repeat the loop until the distance goes to 0. Once the distance has reached 0, the computer does not have to make any correction anymore, but he must keep watching, because then decoherence will make the system jump, and then we'll have to correct for the jumps. In an ideal situation, the field remains in a pure state. It is a little bit technical, but it can be explained simply. If you perform a measurement, you start by a system which is described by a wave function. After the measurement, the system is projected into a new wave function, but it is a wave function. And this succession of jumps produced by measurement are described by what is known as a quantum Monte Carlo trajectory. The system follows a trajectory which has randomness in it, but it remains a pure state. This is what happens in an ideal case, but in the real experiment, the field state must involve the effect of noise, of randomness, which is not quantum, but due to the fact that our system is not perfect. And when we make a measurement, we have a chance of making a mistake, taking level E for level G, or missing an atom, and all these imperfections will transform the wave function into a statistical mixture, but the computer should be able to keep track of all this and compute the best estimate for the density matrix, the density operator of the system. So I gave you the general idea, and here you will see a movie which shows what happens. So you will see a first atom which is prepared inside the cavity, goes through it, undergoes the Ramsey zones, and gives a signal to the computer. The computer decides what is the amplitude and the phase which should be injected in the cavity, and this goes on forever. So you see here a burst of microwave which is being computed by the computer depending upon the result of the measurement. So this is a way, at least a kind of simplified movie of the way the experiment should work. And now I will try to, in a few minutes, to enter into more details so that you can see the complexity of this if you want really to implement it really in the lab. So you have to say a few words about the probe, about the actuator, and about the controller before describing the experimental results. What does the probe do? And this I can describe very fast because it's exactly what we have said in the first part of the 2D measurement. What the probe is doing is to decide which result we will find when we perform the measurement, and depending upon the result of the measurement, you multiply the previous distribution by a sine function which has one sine, one phase, or dephased by pi. And in fact, what it does is just the projection is just given by this mathematical operation. You take the density operator and you sandwich it between operators which are either a sine or a cosine function of the photon number. The trace here at the denominator is just a normalization. And you see that you have two parameters which enters into play. One is phi n, which is just phi naught times the photon number. And this is phi sub r, which is the direction of measurement. This is the phase of the Ramsey interferometer, the operating point of the Ramsey interferometer that you can choose by just changing the relative phase of the two Ramsey pulses. And these operators, ME and MG, are called POVM operators, or are part of POVM operators, or they are called also technically Krauss operators, but these are very, you see, mathematically, they are very simple functions. How do you fix the parameter? How do you fix the parameter? Phi n here is chosen by taking a phase shift per photon equal to pi over 4 so that you can distinguish between 0 and 7 photons, and we restrict ourselves to small fields like that. And now the Ramsey phase phi r is chosen so that the target photon number that you want to reach is just at mid-fringe. So you decide to be at mid-fringe when you reach the target. Mid-fringe means that the probability to find the atom in E or in G are equal when you are at the target. And you see immediately why is it interesting. You see that if the photon number becomes larger, the probability drops to a much smaller value. And if the photon number is smaller, the probability goes to a much higher value to be in state J. Which means that this is a point where you get maximum information. When you detect an atom, you know with the maximum possible information whether you have made a jump upwards or downwards. So you can very well, in this case, distinguish the jumps going up from the jumps going down. So this is a choice we make. We just adjust the interferometer in this way. Second point, what is the field displacement? What do you do when you inject a field on the side inside the cavity? This is well known again by Glauber theory. What you do is that you displace the field. You perform a unitary operation which amounts to applying an operator d alpha, which is an exponential of a combination of the annihilation and creation of photons, with an amplitude alpha, which is the amplitude of the displacement. Alpha is a complex number which tells you in which direction you translate the field in phase space, with which amplitude and which phase. And in our case, in the experiment, we restrict alpha just to real values. So we decide to choose the phase of the field equal to 0 or pi in order to have either a positive or a negative injection. This is controlled by this phase shifter here. And the amplitude of the field, the modulus of alpha, is controlled by the duration of the pulse. You have a source which has a well-defined amplitude, and depending on how long you apply this pulse, alpha will be small or large. And in our experiment, we go from an alpha equal to 0.1, which takes 60 microseconds, to 0.001, which takes 0.6 microseconds. So we're just adjusting the length of the pulse, we can adjust the amplitude of this field. So let's see now how the controller works. Before the field measurement, the field describes a density matrix. What does a width measurement do? As I said, it multiplies the field, the density operator, by an operator mj, which depends upon the outcome of the measurement. This is very simple, but it's too simple. This does not take into account the imperfection of the experimental setup. And I will just say a few words about these imperfections. The first difficulty is that our atomic source, I did not say anything about it, but it's not a deterministic source of atoms. What we do is that we have a preparation of Rydberg atoms, a weak preparation by lasers of the atom into Rydberg state, and there is a Poisson law for the atomic number. In other words, the probability to have n atom in a sample is given by a Poisson distribution, which is given here, which is, we have a probability of 30% to have one atom in the sample, in order to have a small probability to have two atoms. But this means that most of the time, you have 0 atom in the sample. So we have to take this into account. Most of the time when we pulse our lasers to prepare the Rydberg atom, nothing comes out. Sometimes there is one atom, and sometimes two. And we have to take this into account. So what I say here, most probably is no atom. 2 atoms are possible. What happens if you detect 2 atoms? If you detect 2 atoms, you detect either them both in state E, in which case you multiply M by ME, or both in state G, you multiply Mg by Mg, or one in E and one in G, so you get Me times Mg, and you have here a square root of 2, because I remind you that rho is sandwiched between two M operators, and twice square root of 2 is a factor of 2, which just tells us that Me and Mg, or Mg and Me are equivalent. There is no difference in what happens depending upon the order in which you detect the atoms. So this is quite simple. But this is not the only thing. The second problem is the detection efficiency. We detect atoms only in 35% of the time. So there is a high probability to not see the atoms, that they are really an atom and you don't see it. What happens if the measurement is unread? You have fired your excitation and you don't see anything in the end. You have to add the outcome of E and G. This amounts to tracing over an unseen atoms. And unread measurements will transform your wave function, will transform your density operator, but in this way. It's just amount to tracing over the unmeasured atom. And the last problem is the fact that the interferometer has a limited contrast. You see, our fringes don't go from 0 to 1, but they go only with 80% contrast. And this is mainly due to the fact that, in fact, we have detection errors. There is a small probability that an atom, you think that the atom is in E, but in fact it is in G. And this means that you are, in fact, mixing a fringe which with 88.5% is this one, with the opposite phase fringe with a probability which is 11%. And if you add up these two, you get this kind of result. So the limited contrast of the fringes can be modeled into a detection error. And detection error will also have an effect on the system, as we will see. So you see, we have, in fact, three imperfections: Poisson statistics, detection efficiency, and detection errors. And now the computer has to ask itself the following question. Suppose that you detect an atom in E. The computer gets information, I got a click in detector E. So first question the detector should ask itself, was really the atom in this state? There is a small probability that in fact it was in the other. And then it must ask another question. is it possible that I missed a second atom? Possibly there were 2 atoms and I only saw 1. And if so, in which state was the second atom, E or G? So how does the computer answer all these questions? If the system were perfect, the transformation would be just given by this, which I will call rho sub E. So this is quite simple. But now the computer says, in fact, this happens only with a given probability. This is a conditional probability that the atom is effectively in E if I detected it in E. This is a conditional probability which is somewhat smaller than 1. So in this case, I get this result. But there is also the possibility that if I detected the atom in E, it was in fact in G, in which case I would get rho G. And there is also a conditional probability that if I detect an atom in E, in fact there were 2 atoms in E, one that I missed and the other which was in E. In this case I would get rho EE. And there is also the probability that if I detected an atom in E, one atom was in E, but I missed the other one which was in G, and I get this result. And finally, I could be wrong all the way. I detect in E, but in fact the atom was in G, and the second atom in G was missed. And all these conditional probabilities are perfectly computable and knowable from knowing the imperfection. In fact, you can use what is known as Bayes' law, Bayes' argument, to find all these conditional probabilities once you know the imperfections of your apparatus. And you can just, in fact, wire this into your computer, which means that when the computer gets a result, it can immediately compute what is the best estimate of the density operator after the measurement. So you get a clique J, you assume that the real state was capital J, and you have this matrix of conditional probabilities which allows you to compute the projected state. And now the small g and capital J can take 6 different possible values. Either no atoms were observed, or 1 atom in E, or 1 atom in G, or 2 atoms in EE, in EG, or in GG. So there are 6 possible outcomes. And for each of these outcomes, you have a well-defined operation which gives you what happens to the density operator. But this is not all. The computer should also know that from one atom to the next, it takes 80 microseconds, and during this time, the field relaxes a little bit, because 80 microseconds is it's about 1 part in 1,000 of the cavity damping time. So it's a very short time, but you should, since you will accumulate this over a long time, you should take this into account. You have a small thermal field too, and so you have to integrate the relaxation master equation over this small interval. And this is a very simple linear operation that the computer can apply. Now, the computer, not only the computer should determine the state of the system, but it should know what it has to do to the system once it knows the state. So how will you displace the field? You have to choose the displacement amplitude in order to move the field closer to the target. So you have to minimize the proper distance to the desired number state. What is this distance? You have a straightforward definition for the distance, which is just to say that the distance is 1 minus the fidelity, minus the probability to be in the right state. So you see immediately that this quantity goes to 0 when you get in the right state. But the problem of this definition is that other Fock states will give you all a result equal to 1. If you are in a Fock state different from N and C, this term is 0 and you get 1. So in fact, all the other Fock states are at equal distance from the target, which means that if you use this as a distance, the computer will not know whether it is close or far, whether it is at n-1, n+1, or n-3, or n+3, and so it will not know what kind of correction it has to apply. So you have to define the distance in a more subtle way, and in fact, the distance should be a linear combination of the probability to be in various n states, the coefficient of this linear combination depending, of course, upon the target. And in fact, for instance, if you want to have the target n equal 4, you will choose the weights here varying in this way. If you are at the target, of course, the gamma coefficient should be 0 because the distance is 0. But you see that the weights increase when you get farther and farther from the target, which will give a larger and larger weight to photon number which are away from what you want. So the further n is from NC, the larger the distance to the target. And so we choose this kind of map for the coefficients, and these coefficients have to be changed, of course, if you change the target. For example, if you take the target 3, gamma, this coefficient will be 0. If you take the target 2, this one will be 0, and so on. Okay. So once you have defined this, what you have to find is a translation which will minimize the distance of the translated state to the target. So the computer has to compute this function. Now the problem is that this is very costly in computing time, because this function is an exponential operator. It's take very long for the computer to do that. So to speed up the process, we will restrict ourselves to small displacement amplitude, to alpha values comprised between 0 and 0.1. And in this case, what you can do is to make an expansion of this distance up to second order. So you have here the distance of the undisplaced state to the target, a linear correction, and a quadratic correction. And then the computer only has to compute this quantity and this one, which is very fast. And in fact, the coefficient gamma n and c are chosen so that if you are the target, the distance is minimum at alpha equals 0. So you are the minimum of this parabola if you are the target, and you want that because if you are the target, you want the computer not to do anything. On the other hand, if you are at a different Fock state than the target, then this distance should have a maximum at alpha equals 0. This means that if you are at a Fock state which is not the one you want, then definitely the computer has to move you away from this point, and so you need to be at a maximum of this function. And these conditions are enough to choose the values of the coefficients. So you have this quadratic function, and you study it, and you see, for instance, if this function has a minimum between minus alpha max and alpha max, which are minus 0,1 and plus 0,1, of course you adjust alpha to this value. And on the other hand, if the minimum is outside the interval, or if you have a maximum, then it's clear that you have to choose one of the two values, minus alpha max or plus alpha max, depending upon where you get closer to the minimum possible value. And so that gives the criterion, and now I'm just summing it up very quickly. What is the feedback loop doing? You have an atom which crosses the cavity, which is detected. You get a result. From this result, you compute the projected density operator. Then you compute the optimal displacement, which will bring you the closest to the target, according to what I just said. And you apply this field inside the cavity. And then what you have to do is, of course, to apply this displacement mathematically to the operator, to take the relaxation into account, and then you get to rho k plus 1 and you do it again. So that gives you the loop operation. Then the next atom comes, and you see that you have to do all this operation in 80 microseconds or less, which is the time between atoms. And for that, we need a special computer which is dedicated to that, which is called ADWIN. It's an ADWIN system. It's a commercial computer which estimates in real time the field state, controls the microwave injection and the atom detection, which has a very short response time. I give you here the clock cycle. It takes about a few nanoseconds to multiply two numbers. And in fact, it takes about 20 microseconds here, 20 microseconds to compute a displacement. So it's time to apply the displacement and compute it in 80 microseconds. There is a last problem that I just mentioned here. During the time the atom flies from the cavity to the detector, there is space for 4 atoms, 4 samples to be here. And you see that these atoms have already crossed the cavity, but they are not yet detected. And you have to take into account the effect of these unread atoms on your loop. So in fact, you have a kind of delay. It's a feedback with a delay, and it's a quantum delay, and you have to take it into account. So you have 4 unread measurements, and you know what unread measurements are doing, just tracing over the atom. And you have 4 applied corrections, and you have the additional relaxation. So you have to take all this into account, which I just put here in this loop. So you take the finite flight time into account, you compute the optical displacement, you apply it, and you go on. And this is complete. Now, just in a few minutes, I just want to give you the result. The first thing we can do to see that the computer is able to follow what's going on is to operate this in open loop. Open loop means that I switch off the actuator. I just use the computer to look at how the system evolves as a function of time. And I start with a Poisson distribution with 3 photons. And you will see here the detection events. And here's the distance to, let's say, to a hypothetical target, which will be n equals 3. And you will see what's going on. So you start, and you see that the distance is decreasing. And you see here that basically you are in n equals 3. It means that in this sequence of events, the QND measurement collapses into n equals 3. But if you keep waiting, you will see that the distance increases as a quantum jump. And you will see it here, the system is jumping into n equal 2. And then if you wait longer, it jumps at some point into n equal 1. Here. And if you keep waiting, after a time of the order of cavity damping time, you will end up in the ground state. So what you have followed here in real time is the evolution of the field that you keep observing without feedback, and you see that the computer is able to follow the full evolution. Now what we do is just exactly the same thing, but by closing the feedback loop, and we choose here the n equal 2 target. So you see here on this line the raw detection events. And of course, from this thing, your eye, you see it, but you cannot decide what's going on because you are not the computer. You cannot compute in real time what's going on. But the computer computes the distance, and you see the distance is first going down, then there goes some bumps here. These are quantum jumps, but you see that on average, you can keep the distance in a steady state to a very low value. And you see the actuator injections. The injector is very active during the early phase before you get into the right state, and then each time you have a jump, the actuator activates itself to correct for the jump with either positive or negative amplitude. And you see here the estimated photon number probabilities. The target is in green, so you see that the probability to be in the target state increases, gets to a steady state, and each time you have a quantum jump, it decreases at the expense of an increase for the probability to have a smaller or larger photon number. And even more complete than that, so you see here the initial convergence. At this stage, the cavity field is in the target state. Then there is fight against decoherence and back into the target. And you can also estimate, the computer also estimates the full density operator. So we start by a coherent state at the beginning. At some point, we get into the desired Fock state. Then when you have a quantum jump, you see the Fock state is, the photon number is decreased. And during the phase, you correct for the Fock state. Since you inject coherent fields, transiently you prepare off-diagonal elements of the density operator. And all this will appear, in fact, what I have shown here can be shown as a movie here. So now in closed loop, so you see a lot of activity here. And now you are in the desired Fock state. You see that the actuator is off, and you have mostly 2 photons. And you keep watching. Suddenly you have a quantum jump that you are correcting, so there is a lot of off-diagonal elements. And you are back into the n equal 2 Fock state. And it's going on and on. So you see, each time you have a jump, after a short time, the system corrects for the jump, and you come back into the desired state by just observing continuously the system. Again, you jump here, and again, back into n equal 2. So we have done that for n equal 2. We have also done it for n equals 3. So you see here the same kind of traces here, the distance to n equals 3, which goes up and down. Of course, if you increase the photon number, the frequency of quantum jumps increases, so it gives us the limits of this kind of experiment. And this is a single trace, but you can also make a statistical analysis of an ensemble of trajectories, and you can do it in 2 ways. You can stop a trajectory randomly, let's say after 160 microseconds, millisecond, excuse me, and in this case you get the steady state. If you average over a large number of trajectories, you get the steady state of the density operator. And if you do that, you see this kind of result. This is an open loop. After 160 milliseconds, you of course, mostly the ground state. But you see that now that if you close the loop, the probability to be in the desired state increases. It's much larger than it is in the Poisson. And there is another way to look at this, is to ask the computer to stop, not when in steady state, but to stop when you have reached the target. The computer knows when the target has been reached, and it can give you the order to stop, and you make the measurement of the field after the target has been reached. In this case, the probability goes up to 80%. And we did that for n equal 1, 3, and 4. So you see for all the results from 1 to 4, the Poisson law in red, the average value in blue, and the result, which is conditioned to the fact that the controller tells us that we're in the right state in green. So this is all what I wanted to tell you. I will skip this because I have no time. I will just conclude by saying that, in fact, you can do a lot of interesting things with that. And in fact, you can make a variant of this quantum feedback procedure. Instead of injecting a coherent field, you can use atoms to inject fields. So you can have two classes of atoms. One, atoms which are dispersive, which perform QND measurements, and depending upon the result of this measurement, ask the controller to send an atom which will emit a photon in the cavity or absorb a photon on demand in order to bring you back to the desired value. And this is just a movie which shows that. You see here an atom which will cross the cavity. When the atom reaches the first zone, you apply, say, pulse, so it prepares a superposition. This superposition is dephased in the cavity here. Then it gets into the second Ramsey zone, and then it gets to the detector. And then it triggers through the controller a second atom, which is an emitter atom. This means that the atom in level G is sent into level E, and then it delivers a photon in the cavity. And it goes through. And the computer takes this into account, and then send another QND atom to probe what has happened. And depending upon the result, for instance, it decides now to absorb a photon. Then it just goes up, absorbs a photon, and goes into the cavity, and so on. And we have done that. I have no time to discuss that, but these are the results. You see here a comparison between the two quantum feedback strategies. In blue, the result of the previous experiment, and in red, what happens if you control by resonant atoms. And you see that at this stage, we see no difference, but we are trying to improve on the resonant atom. These are preliminary results. So let me conclude. What are the perspectives? Here we have used quantum feedback to prepare Fock states, but in fact we could use real-time quantum feedback also to preserve cat states, Schrödinger cats, by measuring the photon number parity. In fact, a Schrödinger cat is an eigenstate of the parity of the photon number. And when the parity jumps from even to odd, when the photon number jumps from even to odd numbers, this could be observed, and we can restore the parity by adding or subtracting a photon in the cavity in the way I discussed before. Another possibility is to use the computer to perform adaptive QND measurement. Instead of letting atoms go through the cavity and accumulate the information over a large number of atoms without doing anything, you can, for each atom, decide what is the phase and the phase shift per photon which is best to apply for the next atom to get maximum information. So this is an optimization of the detection procedure, and it can be shown that you can count photons with a number of atoms which is a logarithm of the photon number, which is just a for example, 3 atoms for up to n equals 7. And finally, we would like to extend this to manipulating entangled fields in two cavities. I want to stress also that these cavity QED experiments are in fact models for other kind of experiments which are performed nowadays. Circuit QED, for instance, is a field in which you replace real atoms by Josephson qubits and the cavities by by resonant lines, microwave coaxial resonator. So you see here, for instance, a qubit which is coupled to the coaxial line, and this system has exactly the same ingredients as our cavity QED setup, in which Josephson qubits are replacing atoms and the coaxial line are replacing microwave cavities. And in circuit QED, the same kind of experiment can be performed. You see here, Wigner function with negative values, and the decoherence of this kind of state has been studied, for instance, in Santa Barbara. So you can do that with a lot of different systems. Now, optomechanics is also very promising. In optomechanics, you replace the modes of a cavity field by the vibration modes of a cantilever of a small resonator. And these systems are now brought to the ground state, and very soon photon quantum states could be tailored and manipulated in the same way as we manipulate photon states in our cavity. And the same technique of measurement and control could be applied. I just want to stress that there are very different time scales. In our CQED experiment, the time scale is very long. We have a lot of time to perform correction because our cavity damping time is a tenth of a second. In circuit QED, the damping time of the cavity is in the range of microseconds, and the operation time is 10 nanoseconds. So things goes much faster, which is good for accumulating data faster, but it's much more difficult to perform correction because you need a computer working 1,000 times faster than ours. So in fact, we have an advantage in the quantum feedback business. And now I just conclude by acknowledging my co-workers. This program has been a very long project with my co-workers Jean-Michel Raymond and Michel Brune. And these are the names of the students and postdocs which have been involved in this quantum measurement experiment. And the postdocs are Stéphane Cour, Igor Dodsenko, and Sébastien Glaise. And these are the PhD students. There have been a lot of people involved in previous stages of the experiment. And this is a picture of the group taken a few one year ago. I just want to stress Sébastien Glaise and Samuel Deléglise, who did the QED measurement, and Clément Serge and Jinjin Zhu are the PhD students working on the quantum feedback experiment. And thank you, and apologize for the long talk. Thank you very much.
You talked about the need to have a distance function, which was where there was some proportion, some linearity between the photon number state and your target state.
Yes.
And it seemed to me you had to calculate then some sum over of some measurement over all the photon number states.
Yes.
So that means that this non-demolition measurement would have to be made or simultaneously somehow for all these different numbers, or? I mean, that calculation would require you to do several measurements and then do the sum.
No, at each step, the computer computes the whole density matrix. So it has all the probabilities to have all various photon numbers are computed. And then it takes a linear combination of these numbers, which it calls the distance.
Okay. All right.
You mean to take we take into account only the actual value, but we don't integrate the null state. Yes.
Only the
Yes.
the value.
Yes.
Yeah. Is that because I mean there's so sudden changes, or what is the?
The changes are sudden, but it takes some time to record, to witness the change, to detect the change, and then to react upon it. And there is also a delay due to the fact that a few atoms are crossing the cavity between the observation and the reaction.
Sorry, this is a very big question, but do you think these states are already staying coherent them to be very good and useful for the applications you want them for?
No, it's clear that the fidelity that we have here is limited. You know, we talk about fidelities of 80%, and we are very far from what we need really for applications. But this is a matter of technology. We can improve. We know that we can have better cavities and that we can react faster. So we could improve this fidelity to the 90–95% range. But even that, in fact, we don't have, with this system, we don't have good application possible because the qubits are flying. It's just a system for demonstration for proof of principle. Yes.
Is there any use to have more photons to prepare more photons?
Yes. The problem is that if you prepare more photons, they will decay faster, and you will need more atoms to count them. So there are two curves which cross each other. If you increase the photon number, you are at a point where you cannot detect faster than the photon decay. And here the limit is about 4. We could get to the value of the order of 10, maybe 15, but it's, of course, with this kind of system, you can go to hundreds of thousands of photons.